record on this computer. And I should tell you why I think this is important. Make sure I am recording. Yep, I'm recording. I noticed while I was teaching my introductory course, my PHY322 course this morning, that periodically I would get this little pop-up on my screen that says my internet connection is unstable. That could be a problem, in which case my voice might be all messed up and you might not be able to see the video anymore as I'm transmitting out. Obviously, it'll be recorded. I put it on my, I have a YouTube web channel, and it's going to immediately show up there. And so I don't have to keep giving you the address for my YouTube channel and any of our lectures. And so you don't have to figure out which are for PHY322 as opposed to PHY112, or any of the volleyball junk I got on there, or some of the physics demonstrations I have put up there. I post the link onto Canvas, and hopefully I'm showing my Canvas screen. And I just want to remind you that should there be a need for you to look and watch the video in an asynchronous mode on your own time, it's right here. Okay, that's the Monday and the Wednesday lectures. As soon as class is done today, immediately after I'm done, Zoom turns the presentation into it's an MP4 format. Actually, I'm not savvy enough to know the difference between MP3s and MP4s, but that's what it gets us. So if you have a way to play it, and I think Canvas has a player, you just click on this link right here, it opens up, and there's a lecture. You hit the button just like you would in YouTube, and away it goes. Okay, so I want to make sure everybody knows that's there. I also think that you need to be fairly attentive to the assignments link in Canvas. That was homework 6, which I think just about everybody has uploaded. And of course, here's the tutorial that we've been working on. It is actually, you can see, due today at 5 p.m. I had office hours yesterday, and 2 people came. One of them's actually done with it, uploaded it. If you're looking at how to do these tutorials, I'm hoping that many of you are realizing, because you're reading the book, that often the tutorial is just what either is in the book, in the reading, follow along some of the steps in that particular area, or it's what's on my PowerPoint, or it's what's in one of the handouts I've given you. And so if you don't know exactly where to start, maybe that's a good place to look. Office hours, of course, is another place to come and get help on that. Okay, and so I think you want to pay attention to those dates. We've got a new topic today. We're going to be talking about statistical interpretation, and that'll be due next Wednesday on the 1st. And then right there, I'm getting my internet connection is unstable right now. So let me take a quick look at it. Yep, it's still my home Comcast account. Looks like it's back now. Generalized uncertainty is what we'll be talking about on Monday, and that tutorial will be due next Friday. You'll notice there's no direct homework. There probably wasn't going to be any this week, even if we were meeting face-to-face, but that is kind of the schedule for the next, until the end of next week anyway. There is one more tutorial from Chapter 3, which we'll be talking about and putting out next week, Wednesday. It'll probably be due the week after that. Then eventually there'll be some homework on chapter 3, this formalism stuff, and but that'll be due the week after that. Now, I do want to talk about a policy that I have, because one thing you got to recognize is this is a little bit more difficult than just showing up in N210 to talk. I have to do a little more preparation here, and I want to talk about due dates, specifically the ones that are put out here. Now, my policy does give me the right to take 20% off if it's late for each day. Okay, and this is, I think, we're at a point right now where we're doing this online business for the rest of the semester. Keeping up with your work, because you don't have the ability to ask questions as freely. You know, I may not see you raise your hand. I've got 2 screens I'm scanning between, trying to produce this stuff. I think it's more a greater burden, let's just say, is put on you to stay up, so that you know what I'm talking about, because I might not be able to answer your question like I would in the classroom. I generally don't invoke that. In fact, I don't think I've invoked it at all this semester, but the 20% is meant for me once I'm done grading an assignment. Like, I'm done grading matrices tutorial. right? And so if you're one of the few people, and there may be one or two people who haven't turned it in, okay, now I got to go back. I'm done with matrices. That tutorial is done in my mind. I've moved on to like the tutorial we're going to be doing next week. That's where my focus is. If you make me come back to an old material and bring it out, and oh yeah, that's what we asked in that question, as if that's what I should be working on. You're dragging everybody else behind, and so unfortunately, in that case, I'm going to have to invoke my 20% per day rule. Okay, and so that's generally where I put it in. I haven't started grading homework 6, but that's going to happen right after class today. I have about 3 things on the work list to do this afternoon, including office hours, but I'm going to be grading homework 6. Once I'm done grading homework 6, if you're one of the few people that haven't turned that in, okay, you're kind of hiding under the cover of my inefficiency to grade it as soon as it's turned in. But once I'm done grading homework 6, anything that's turned in after that has to be late. And I know Canvas has a due date and it turns it pink. I ignore that until such time as I'm done grading the assignment, and then I will be starting to have to deduct 20% just to make sure that everybody stays up. And I hope that you see that as not unfair. I do want to talk about office hours. I scheduled it for 3 o'clock yesterday. I didn't get as many people as I thought. I was very happy for the 2 that did show up. Thank you. I hope it worked for you. In that hour, I think, maybe you got most of the tutorial, which is due today, done in both cases. So the 2 people who were there. I worry that 3 o'clock is a bad time. I think I may have told you this before. At Washington College, mostly to protect your privacy, I think, I'm not allowed to see a lot of the basic information about you, like your schedule, for example, what time zone you might very likely be in right now. That was kind of an interesting thing. I have some of my international students in the introductory class that are somewhere in the Middle East right now, and I'm doing their 9 o'clock class, and they're telling me, oh yeah, this is it's just after dinner, it's during dinner, or something like that. And so I don't know anything about that. I don't know what your schedule is. So when I pick a time to do office hours, I'm just pulling a time out of a vacuum. Let's just say I could be pulling it some other places. I'm sure you can come up with more colorful expressions, but that's the deal. And so if 3 o'clock isn't working, let me know. I'll move it to 4. And oh yeah, if you've got a 2:30 class, for example, and it doesn't get out till 3:30, feel free to join the office hours until the time as I leave. And I normally schedule them for about an hour, but if there's people still asking questions, I'll hang around longer. Okay, and I think we quit yesterday at office hours at about 4 o'clock. But if you chimed in like sometime near the end of it and I was still there, we'll continue talking based on trying to help your schedule. Bottom line is I'm not going anywhere. So I'm here to help you. I'll go down and shoot some pool or ride my stationary bike or whatever I got to do to have some fun this afternoon. We're binge watching. My wife is binge watching Homeland. I was watching an episode with her last night. That's all I've got. So, and if you do need time, you do have a question, you could try and set up a Zoom meeting with me if I'm available. And like I said, we're not going anywhere. So feel free to find yourself getting help as you need it. So I'm going to schedule. I've got my introductory class. I'm going to do office hours this afternoon with them at 1 o'clock. And I'm going to keep the 3 o'clock time for you all again this afternoon. Again, with the homework being done, or the not homework, the tutorial due at 5 o'clock. I'm hoping that'll help you get things done. All right. And you pay attention to these schedules because obviously I uploaded the tutorial for today this morning, okay? And you might want to open it up because I'm going to go over one of the questions before I quit today. So that'll be statistical interpretation. Monday's tutorial is posted right now. It's the generalized uncertainty principle, and we'll be showing that with some high power math and commutators and things like that we've learned about, and that's what we'll be doing on Monday, okay? So without further ado, then I'm going to swap over, stop sharing this, and we'll share instead. Let's see, what do we share? We'll share the PowerPoint, and I'm hopefully getting a little bit better. Did that take? It didn't seem to take. Let's make sure we're sharing the PowerPoint. Share screen, PowerPoint, share. All right, and we'll go to full screen. I'm getting better at figuring out how to write with my mouse. All right, you aren't doing its thing though. There we go. And one of the things you should recognize, and I'll get rid of our pictures so that it doesn't interfere with the video that we post. There it is. Your internet connection is unstable is what it's telling me right now. So hopefully my voice, when I do that, I try to slow down my talking when it shows up like that, just so that if it is being interrupted or staticky or whatever, you don't miss anything important. I think one of the things you should understand about what we're doing right now is there is really nothing new. All we're doing is taking the things we did in chapters 1 and 2, all the example problems we did in 1 and 2, and we've completely changed the notation and generalized some things. Okay, we're looking at the very specific applications that we did in chapters 1 and 2, many of which we also did in modern physics. I know my class did a number of those, and I'm hoping that those of you that had Professor Campbell for modern physics did some of those same example problems. And now we're trying to put it in a more general sense to give you well, what is this quantum mechanics all about? Okay, and we've changed the notation completely on you, haven't we? And so let me get my pen going. And so we've got this idea of a wave function or an eigenfunction or an eigenstate. We've got multiple words that describe the same thing. And we said for a particular operator, there is always an eigenfunction, okay? And then any other, which is a particular state, it's a, you might even say from yesterday's tutorial, it's a determinate state, okay? This particular state, if you make the measurement of whatever the observable is that's associated with the operator, if you're in a determinate state, okay, which we sometimes refer to as the basis, you will be guaranteed to make the measurement of the eigenvalue as the expectation value of that operator. Okay, that's what a determinate state means. On the other hand, though, it is possible that a system might not be in a determinate state. It may be in some superposition of a determinate state where these coefficients associated with each of the determinate states represents a probability that the particle might be in that particular state. And so you can set up an experiment where you kind of guarantee that, for example, in the infinite square well, that's what the state's going to look like, infinite square well, right? That's going to be what psi is for that particular state. Or another determinate state might be, I guess I'm wondering if I should give you psi or psi squared. Okay, who's writing up in there? Don't be doing that to me. Maybe I should be going psi squared, which looks very much the same. Thank you for erasing. You've figured out I'm sharing with you. The next state might be this one, right? And I'm not drawing really well there. The next state might be something like this. And again, not well drawn, but remember that's, if I'm drawing psi squared, remember psi would have looked something like this, right? For the infinite square well. And you know, we've seen these, they look a whole lot like the standing waves on a string experiment back in an introductory class. And so I did figure out how to make the eraser work too, go figure. So I can get rid of this guy if I don't like it. And I can erase you if you come back and start writing again with me. All right, go back to the pen, it's Control P. Anyway, so we can create these states. And the question, of course, is how do I get the coefficient? And the answer is, this is the notation for it now. We say we do the inner product of the state, the determinate state, with whatever the initial condition is. And, you know, in chapter 2, I guess we would have written that. We would have said that. And we would have said, okay, this is one of our wave functions for the infinite square well, say, or the simple harmonic oscillator, or whatever it was that we were trying to find the coefficients of. So that's how we find the coefficients. And you can see why this is nice shorthand notation. That means you got to do that, right? That integral, you got to do it. Okay. Now, you might be asking yourself, okay, why do I use this F? Why do I sometimes use psi? Why do I sometimes, what were we using the other day, G, right? Or F? Or sometimes you see an F sub P. And you got to remember that Schrodinger's wave equation is a special case of an eigenvalue equation where we have this operator. And so far to date, we've had 3 operators, right? We've had the momentum operator. The momentum operator was minus I h bar, the derivative with respect to x, right? That's one operator we had. Okay, another one we had, very kind of trivial operator almost, the position operator. And then, of course, the energy operator, which, you know, for reasons that you saw when you were in Kaiser's mechanics class, we call the Hamiltonian operator. That's why we give it the symbol H, but it's an energy operator. And let's see, it was minus h bar squared over 2m. And then right now it's a one-dimensional derivative, second derivative, right, plus a potential. Okay, so those are the three operators we've used, and we're symbolically saying, hey, one of those three right now is this operator Q. Of course, the states here correspond. We've given these things different names conventionally. It doesn't have to be, and then you just go to the worksheet and we give it a whole different set of names. But last class we called the eigenfunction associated with the momentum operator, we called it F sub p, didn't we? P being a subscript for momentum. I think we called this guy, for whatever reason, G sub y, is my recollection. I forget if I subscripted with a y or not, but that was the eigenfunction that we were using if we were trying to find the eigenvalue equation for position, which I went over very quickly. I do recall that, and so if you want to review it a little more detail, you can just go to it's, I think, example 3.3 is the example in our textbook. It does this problem because it is almost trivial, right? Once you've accepted a continuous eigen value as opposed to a discrete eigenvalue, the position, then you have to accept Dirac I have trouble with that word, orthonormality as an answer in lieu of being in Hilbert space and actually being normalizable. You have to accept the Dirac special case of that, and you're good to go. And then I guess just the last point, the Hamiltonian, we've always called it this, right? Psi has been the eigenfunction for an energy eigenvalue problem, which Schrodinger's wave equation is a special case of. It's the energy eigenvalue problem. All right, I'm going to slow down. It's saying my internet connection is unstable. Of course, we sometimes tried to make the point, I guess, this might be psi sub n here. There, that's an n. And so you saw in the tutorials, a lot of times we'll just write that, okay? And that's perfectly acceptable notation. You notice I've done the same thing with, I guess this could be momentum, or it could be position if I just turn this guy right here into an F, okay? And so I could do the same thing here. I could be referring to the nth one, because there are multiple ones, like n equals 1 over here for the infinite square well, right? N equals 2 over here, n equals 3 here, right? Those are all n equals 3, that's an n. It looks an awful lot like an m. And so anytime you're using this ket notation, people like to abbreviate. And on some of the problems, when we were just talking about vectors, we used I and J, didn't we? And you got to be generalized. You could think of them like unit vectors in three-dimensional space, but we're really thinking of them more as basis vectors, eigenstates, which are not changing. They're the kind of the things that we take multiplied by components to get any other state. Those things, you have to kind of come up with the notation, and you can think of them as unit vectors, but they're really not, because they're more than just 3 of them, I guess, is the reason there's more than you got to think about it that way. All right. And so everything I've got on this slide so far has been for discrete eigenvalues, in which case you find Fourier coefficients, right? Fourier's theorem is critical to understanding states that a small particle could be in. And there is somewhat of a reason for that. Historically, if you look at the early people who were trying to describe quantum mechanics, they were often acousticians. And those of you that were in acoustics class realize that, Fourier transforms and Fourier series are key to acoustics. And so it's almost natural that, since that body of knowledge existed in the 1800s, that as quantum mechanics came to be developed in the early 1900s, that the language people would initially be using would be that of acoustics. Of course, Dirac comes along, and he's more of a mathematician, a linear algebra kind of guy, and he recasts a lot of this so that Schrodinger's wave equation, which is almost an acoustic looking thing, can be written as just an eigenvalue problem that mathematicians had studied for linear algebra way before quantum mechanics was even thought of. Okay, and so he adapts another. And then as you move through the 1900s, the two things kind of merge together. And that's what chapter 3 is really all about. Nothing new that we didn't do with Schrodinger's wave equation, as if we were taking a mechanics class but it's, applying to things that are very small. Okay. And then we're just melding it in with some new math, and hopefully we can see some general principles that pull out. And, I will say one thing that about this eigenvalue equation that I noticed as I was grading some of the homework. A lot of you aren't confident enough to do some things that I think you should. And so I guess let's just say I took one of the operators, I don't know, maybe think about it as momentum, right? And you're doing something like this. The operator in your mind, I wrote Q, but think about the momentum operator where you took a derivative, okay? And then you're operating on another eigenstate, okay? Realize once you do this right here, because of the eigenvalue equation, this is an integral. It's an integral just like this thing is that integral, right? I don't have space to write it out here, but the result of this, and I'm a little conflicted because sometimes I like to put a line right there because Q is operating on that state. I see in other textbooks, Q is just operating right on the state without the line. I'm a little duplicitous on whether or not I think there should be a line there. I do it both ways, and I say both are right. But the bottom line is the eigenvalue equation tells you that I can substitute right there, the governing eigenvalue equation, what the eigenvalue is, okay, for the operator. So this is absolutely equivalent to little q, okay, times the wave function. Okay, now at this point, it's no longer a math function. Eigenvalues are constants. Like you measure for energy eigenvalue, you measure 3 EV. Hopefully you realize in an integral, which this is a shorthand expression for an integral that looks a lot like this, you can always bring the constant out front of the integral. So this just becomes Q times psi. Now, assuming these things are orthonormal, and in general, this might have a subscript n, and this might have a subscript n. If m and n are the same, well, this just becomes equal to q, right? If they're not the same, well, you got to throw in that Dirac delta for m and n. And what I saw was a hesitancy, and this is kind of the point. Once you've applied the eigenvalue equation right here, okay, and you reduced it to the operator operating on a function to a constant multiplied by a function, don't be afraid to bring that constant outside the integral. And as a constant, it can be put wherever you need it to be. If it's still subscripted, you may not be able to bring it outside a sum, but you can certainly bring it outside this integral. And then, of course, always be looking for the ability to substitute something like this for the orthogonality relationship and replace it with a Kronecker delta, and then perhaps kill a sum. And that's something that I was watching people hesitant to do when we were just doing the tutorial on the Dirac notations, and that's part of what this is about: becoming familiar and confident enough to make that transition. Any questions on that before I move on? I only have 4 slides and I'm going to do an example problem, so that's why I'm being a little bit more wordy today. But I did want to just kind of give you the big picture before we move out. But the bottom line is, any function, any state, I guess, that you can put a small particle into can be made up of these discrete states that exist, okay, as long as the thing is bound, okay, and we're talking about the bound case, not the continuous right now. Some superposition of these things where you have to figure out what the coefficient is that you multiply by the individual states. And we're going to talk about, well, what do those coefficients represent in this statistical interpretation? And again, nothing new. I remember vividly, you may not, but saying exactly these same things about the specific case of the infinite square well when we were talking about it a long time ago, back in chapter 2. Okay, so the first thing is, well, what do we interpret c sub n squared at? And I know you remember this because you all did it on homework problems. And specifically, we were always talking about energy, right? So we were always talking about the size, but it could be something else, some other state. We meant psi to be the eigenfunction for the energy operator, okay? And that's what we were talking about back in chapter 2. Now we're realizing that there's other operators we might want to be talking about, position and momentum. And I think the reason we're being more general right now is we're going to pave the way in 3 dimensions for talking about angular momentum operators and z component of angular momentum operators and spin operators, because all of those things help us describe small atoms and maybe even molecules. We'll pretty much be stuck with hydrogen and maybe a little bit beyond that. Anyway, so I think on the last slide, I said something like psi must be equal to a sum over either n or m. And generally, I like to go n with the ket and m with the bra, but that's a preference, okay, of c sub n times whatever the determinant state is, that particular eigenvalue that is the basis that we can multiply by a coefficient and add up to get any other state that we want. And so I guess what I've written right here is that sum and that piece and that piece. And of course, we're going to multiply it by the bra version of the same thing. And at this point, I hope everybody realizes that's a lousy looking psi. Okay, that's going to be equal to a sum, and I've just changed the index now. I'm going to go with m, and that's my preference generally, and I think a lot of people do it. M is the bra and n is the ket as a general rule. If you don't have any other, you can use whatever you want, quite frankly, but this is what a lot of people do. And so that's the coefficient that is, I guess, I better give myself some more room here. And I figured out how to get the eraser. Look at that, there's a little, no special fast function, but I can erase that. And then I can go Command P to get my pen back. And I guess I got to do that. And that's subscripted with an M. Now there's one thing missing here. Before I go on, what did I forget to do? And I didn't actually forget. What's not done here? Somebody shout it out. What's missing? It's about this C sub M. What's missing?
The complex conjugate.
There you go. Well, way to go, Jacob. Thank you. Yeah, I need a complex conjugate because the thing that's in the bra, I'm writing that guy right there, always has to be the complex conjugate, right? And so we're doing something that I hope it's not surprising to anybody, but if I do the inner product of psi, this psi right here is a psi star, even though the notation doesn't require you to write it. There should be nobody in the room, I'm hoping, in the Zoom room here, that doesn't realize that better come out to be 1, right? Has to be, okay? And so let's erase some of this stuff that I've been putting on here that's just making it harder to visualize, perhaps. Okay, I used to be able to get that eraser up here. All right, why are you not playing? There it is, eraser. So I can get rid of some of this. I've already pointed out what they are. Okay, so I'm going to do this operation here, the inner product of psi and psi star. And I put the n piece right there and the m piece right there. And I said, these coefficients, they're constants. I brought them outside the integral, didn't I? They're not associated with the integral at all. I just put them out front. And I left that guy right there. Okay, now hopefully, let's get my pen back. Hopefully you realize, as I said on the previous slide, that right there is just the Kronecker delta, right? So I multiply these two things together. They are integrals because that's what this pointy bracket means I'm doing here, but I'm only writing the sum which is inside the integral. I'm basically writing the integrand out without a differential, without the integrand signs. And I realize if I can get two things like those together, I can replace it with the Kronecker delta. The Kronecker delta requires that m is equal to n, doesn't it, for this to move on, in which case that m right there and that n right there become the same, and one of these sums is done. Right? Because there's only, in this sum right here, there's only one value from 1 to infinity where m is equal to n, and that's the only one that gets kept behind. And so what I'm left with is the product of those two things, right? And this is one of the other things I saw when I was grading the Dirac notation. There was some hesitancy on you to simplify, for example, a star times a, and maybe it had a component associated with it. I had a lot of people leaving it like that. My answer would be, you really ought to take that and demonstrate that you know that's what it means. It means the magnitude of those two things squared. When you multiply something by its complex conjugate, you get its magnitude squared. And it's not just a kind of a math step, it's a what's going on in your head. What are you thinking about right there? This becomes a real number squared, doesn't it? Okay, and so I guess the point here is once I've done that, I'm saying that that real number, the Fourier coefficient, squared, when I add up every one of them, they add up to be equal to 1. And I think this is what we're going to say here in a second, for a particular eigen, I'm sorry, for a particular operator, and maybe I should do that just to be definite about what I'm talking about right there, and then I'm finding the expectation value. I do find that there's a lot of sometimes people put the little operator hat there, and sometimes it's just presumed because it's obvious. It's got to be an operator. People drop it. Okay, same thing right here, right? That's an operator. You find if you do that, and again, remember, see, I drew the line this time, right? What we're saying is now we're going to do this to that guy, right? And that's going to give us this function right here. Okay, see what I did? I put Q and I operated it only on the N, only on the ket part, right? And then I did what I said we should always try to do once you've applied the eigenvalue equation, that I can bring the constant outside the interval, okay? And that's a key step. You've got to be kind of confident enough to go, yeah, I've applied the eigenvalue. That's how I evaluated the operator of Q onto the eigenfunction. I got the eigenvalue, which is just a constant, a number. And then I brought it, actually, I drew it from there. It actually was sitting right in there, wasn't it? That's where it was sitting, and I brought it out front. And now what's left is this thing. And you've got to be in the habit of seeing, hey, that thing is the Dirac delta. And again, all of this is how you handle discrete eigenvalue cases, where Q sub n here, associated with state 1, there is, for example, E1. With state 2, there's E2. State 3, there's E3. And we saw that over in, well, a couple times anyway, with both the finite, with the infinite square well, the simple harmonic oscillator. Inside the finite well, we saw that same sort of thing. Even inside the delta well, we saw that. But if you remember in the delta well, I think there's only one state, right, that can exist in an infinitely thin well. Anyway, so that's what we've got. Remember, this guy, when m sequences all the way from 1 to infinity, there's only one value in that sum, where m here is equal to an n. Okay, that kills that sum, is what we like to say, with the Dirac delta. And of course, all you have is this thing being the amplitude squared multiplied by the eigenvalue. And the interpretation of that, I say here in the bullet below, so C sub n's function is expected for probabilities. You may remember I said, okay, in one of the homework problems, what is the probability that you're going to measure E1? And you found C1, and you squared it, and you said, well, whatever the value of C1 squared is, that is the probability that I'm going to measure the energy eigenvalue. Because I think every time we did that, it was for energy. That was the probability you might measure E1. And so if it is possible to have multiple states, all you would do is you would take a particular energy eigenvalue and multiply it by C squared. If there are a mixed state, you have multiple states existing, the expectation value is kind of a weighted average of each of the individual eigenvalues that might exist, okay, with the weighting function being the Fourier coefficient squared. If you happen to be in a state that is a stationary state, we've called it a determinate state now. If you happen to be in one of those states for the system, like that one for the simple harmonic oscillator, well, C will turn out to be 1, right? And there'll be 100% probability that you'll measure E1. And that's how we interpret that, okay? We did have a couple homework problems, if you look back, where the C sub n's turned out to be functions of time. And so you might have to include that factor if they're changing in time. And that happened a couple times for us in some of the homeworks. Okay, so that's our interpretation. Hopefully nothing new there in terms of an idea, but completely different notation, obviously. And when we were doing this previously, we always only thought about the specific eigenvalue problem dealing with energy, and we were always operating on a wave function that was like that. And we said the eigenvalue was always E times that same state. And the only thing I might do is I might go E sub n right here to generalize it out. But that's Schrodinger's wave equation. And we solved it for a number of problems to kind of demonstrate that this happens over and over and over again. Okay, questions there, interpretation. And is there anything new? Hopefully not. New notation, absolutely. Generalize this out though. It could be true for position and momentum, and moving into chapter 4, it's going to be true for angular momentum and the z component of angular momentum, perhaps. And so continuous eigenvalues was the other. We've so far, everything I've said had to do with discrete eigenvalues, okay, where the energy was either 3 volts, 3 electron volts, or 7 electron volts, or some periodic relationship. And remember, like for example, the infinite square well, it was a bunch of constants over n squared, if I remember right. Or was the n in the numerator? I forget. No, the n was in the numerator. Let's make that go away. It was h bar squared. In the denominator was 2m times the width of the well squared. And so I think it was n squared up here, pi squared. And so that's how the energy eigenvalue went in that case. Okay. And so that's what I meant by discrete, something like that. Or for the simple harmonic oscillator, I guess n plus 1/2 times h bar omega, right? Discrete. But we talked about momentum all of a sudden, and now we didn't have discrete eigenvalues. We had continuous eigenvalues. And in that case, we found that Dirac orthogonality, orthonormality required that there be a Dirac delta involved. And I think, let's see, I can write, rather than writing a state like a sum, I'm going to change to writing a state, not a sum now, it'll be something like an integral and let's see, I might do something like this. Well, now let's change that for real quick. Eraser, because whatever the function is, I might, let's go my pen back. I might write something like, so maybe I'll write an F, okay, and then I'll put it in some basis, and then I'll integrate over, say, X, as opposed to what I said over here. I'm trying to make an analog to this thing right here, okay? And there you go. And so this is kind of like the coefficient C sub n. Okay, and this is the state, one of the eigenstates I've talked about. And so now this thing is allowed to be continuous. It has to be inside the integral. Well, I think we said there's going to be something like a Fourier coefficient. We have to take a state, and maybe I should have written this as psi to match up with this. I'm going to take another state, and I'm going to do the integral. And the great thing about Dirac orthogonality is it just plops that guy right in there on the integrand. And notice that's my answer. Integrals are almost trivial, but they have physical significance when you do something like that. And so I guess I'm saying that this thing that's like the Fourier coefficient is just some eigenstate. And the interpretation, though, is important. Remember, almost on day one, we said the probability of finding a particle in some location, right, can be found by doing this. You take the answer you get, okay, you square it, and you integrate between the two locations, and that's the probability that we're going to find the particle in between those two locations. Well, here I think I just showed that that thing that's like a Fourier discrete coefficient, that thing can be squared, and it operates in exactly the same way. And so this guy right here, which I just called as an F, but now I'm going to restate. I'm going to call it C right here. That's the function I'm talking about. That guy right there functions exactly like psi squared did, okay? And so I just multiply by a particular state, and instead of having a sum of a Fourier coefficient times a state, I've got a continuous function that is multiplied by the state. And then rather than summing over a discrete number of values, I integrate over some range. in general minus infinity to plus infinity. If I'm trying to get a probability between 2 points, I just integrate between those 2 points. So I think that's that is consistent with what we did for discrete cases. We've generalized out to the continuous eigenvalues. And remember, free particles don't have discrete eigenvalues; they have continuous eigenvalues. But we're consistent here in what our interpretation of these C things are. Okay, good. Last thing I guess I want to say, and then I want to go out and do a problem, is we found the momentum eigenvalue, eigenfunction, eigenstate the other day. We actually solved a differential equation. It's a first order differential equation to solve. We solved this thing, okay, is what we mean as the eigenstate for the momentum operator. And so, for example, if I'm looking for this thing that's like a Fourier coefficient, but it's continuous for the momentum case, I just do this answer right here, right? And that means take, I guess, 1 over 2 pi h with a square root, because I got that piece right there. And then I slap this guy right in here. Now I want you to notice one thing: negative sign right there, no negative sign right there. Can't say it enough. That's because the state is in the bra position, which means it's the complex conjugate. And then all I have to do is multiply by whatever state I have, and that should give me this thing that's like a Fourier coefficient, except that it's continuous. And so I'm going to give it a name in a second. And so now I have to say silly things like the thing that's like a Fourier coefficient, but it's continuous for now. By the end of the slide, you'll see it'll have a name. Okay. And those of you that have studied acoustics, who took my class, or who have even just thought about this, you should kind of recognize this, because we talked about it when we did the free particle. We said, okay, if you know the initial condition, you can figure out this thing in what I hope I referred to as K-space, okay? You know, where you're not looking at the x-axis as being x, but you're looking at the x-axis as being the wave number, okay? And we said this is the Fourier transform. And then if you happen to somehow know this because you have a device that can measure that, sometimes, you know, if it's in time, we call it a spectrum analyzer. My internet connection is showing up as unstable here. I guess if you know that, you can do the inverse Fourier transform of that and get the state back. And if you see what we're doing here, the only difference that I see really is that H bar right there. And I can explain that away based on the fact that here I was integrating with respect to K, and now I'm integrating with respect to P, and you can see those things differ by that factor of H bar. And so it isn't unusual that I would have an H bar square root up here and an H bar square root up there. And so I guess this thing looks exactly like that. I've substituted that for momentum over H bar, right? And by the way, this is de Broglie. We have this equation thanks to de Broglie and his observations that we talked about in modern physics. You can see that this guy right here is what I'm calling C sub P up when we were talking about the thing that's like a Fourier coefficient, but is continuous. Well, we're going to give it a name now. It's called the momentum space function, okay? And it's designated phi, capital Phi, just like we designated lowercase phi over here. And that's what we can do, okay? And the significance of this thing, well, first of all, if you happen to know it somehow, because you're able to make a measurement of it, and you want to get the psi wave function back, you do the inverse Fourier transform. But more to the point for momentum, if you're trying to find the probability that something has a particular momentum in between momentum values of A and B, well, in position, we took the position wave function and we went from A to B and we integrated over Y. We wrote it like this. It should make sense that we take this momentum space wave function, slap it right in there. It's C sub P, if you like. You square it, you integrate over that momentum. That has to be the probability that the momentum will be in between the values A and B of momentum. And you're integrating over P instead of integrating over some coordinate X or Y or Z or something like that. So that's the significance of this momentum space wave function, which is like a Fourier coefficient, only it's continuous, not discrete, and it tells you something about your eigenvalue. All right, hey, that's all I got for this. I want to jump to a problem that I'm going to do in the last 5 minutes here that Let me unshare that with you now. Don't discard my scribblings. Come on, you can do it, computer. There we go. Boy, that took longer than I was comfortable with. I was worried we were going to not come back here. All right, let's click on this guy and stop sharing that. And I want to share my whiteboard with you. Oops, my one on my tablet. Share it. And yeah, certainly. Screen sharing, screen mirroring. Yep, good. Go away. Go away. And that's just my notes from before. 3 p.m. office hours today. Don't forget about being late with your assignments. And I want to pull you over to today's worksheet. And it's problem 5. And I have to be honest with you, as I was doing problem 5, if you look at 1, 2, 3, and 4, problems 1, 2, 3, and 4 pretty much follow from exactly the notes that I have. It follows exactly the textbook. Then we get to problem 5 in this tutorial. And I was like, well, there's very little chance that somebody would do it. But what I want to do is derive that relationship we just came up with. All right, look, I got 112 students submitting stuff. That is this, this momentum space wave function thing. I want to show that it has to be equal to 1 over the square root of 2 pi h bar, okay, times the integral from minus infinity to infinity of e to the minus I p over h bar times x, okay, and then times the a wave function x and t dt. I want to show that, and that we call this the momentum momentum space wave function, and it really is just the Fourier transform of this guy. But the importance of it is it represents probability that we'll find the momentum in a particular region, right? That's when you square it anyway. And so I want to do that. And the way the problem has you go about deriving this thing is it says, all right, start by writing psi in the position basis. And those were words that I don't think Griffiths used. And so I want to make sure that that's clear what that means on problem number 5 here. I think that means, and you can write it a couple different ways, but I think we're saying that the integral from minus infinity to infinity, remember this is a continuous Fourier coefficient case of this guy, multiplied by some state position, x, okay? And then we're integrating over x, right? And remember, it may bother you that I put that in here. And we said for position, that thing that's like a Fourier coefficient only difference is exactly equal to psi, right? We go back to Wednesday's lecture, we showed that. And so I'm putting that right in, and I'm saying that's how I can expand out. This is like C right here. I can expand that out, and I've got the determinant states, and I'm integrating over all the places. And so psi here represents how much of each position state exists. And then the problem goes on to say, okay, use the identity operator. And remember how we defined identity operators in the tutorial that we just did. We defined it as this kind of wacky function here, where you go the two momentum operators facing each other. And you did it with position, I and J or M and N. Only in this case, I guess we're saying that's enough because these are operators. There's only one momentum. I don't necessarily have to go X and Y coordinates. I'll just have to integrate over all momentum. And so that's how we're going to define the identity operator. And you should recognize this guy right here from the tutorial you did and you turned into me. And I'm going to put that in my function here. I'm going to put that into here. And then I'm going to turn the crank and see if I don't get what we need to do up front. And so to a great extent, this is an exercise in how to do these functions. Now, realize once I put the identity operator in here somewhere, I've now got a double integral, don't I? Because initially I was integrating over X because that's how I was expanding out my eigenstate to consider multiple position states, okay? And I'm throwing this guy in here, so I'm integrating over momentum. And so you kind of have to kind of watch what we're doing. And the general thing we said as a definition of this guy was you take the momentum operator and you multiply by this guy on the inner product, and that's an integral, right? Okay, so let's write that out. Write that out. Let's see. That means I'm doing the integral of P prime, and then I guess I've got this piece right here, because that's what I mean by that guy. So I've got psi, oh, and I need a, I guess I need a bra on that guy. I need psi x of t, x and t, and then I need that thing brought right down, right? And then I've got dx. Okay, great, minus infinity to plus infinity. And then I'm going to insert the as I said, the identity operator into this. And I get, let's see, big long thing now. I'm going to integrate minus infinity to plus infinity of P prime. Okay. And then right here, I'm going to insert the identity operator, because why not? I can put the identity operator anytime I want in any place, because it's just like multiplying by 1. And that's that integral with these two p's pointing towards each other. And then that integral is over dp. And then I've got the rest of my function that I've started out with, which is the definition of this momentum space wave function. And so I got to go psi x t, and then I've got to go x, and I got to go dx. And part of me wonders, should I have color coded this? See, there's an integral right there over p associated with that guy, and then there's an integral over x associated with that guy. All right, so what can I do? What can I do? Well, the first thing that seemed fairly obvious to me was to combine that guy up with that guy. All right, so I rewrote this, and I'm going to race up at the top in order to do this. Give myself some room. And all I've done is I'm trying to solve this. All should be equal to that guy. Okay, and so I'll bring it up here, and I'm going to rewrite the order. I'll put both integral signs out front, and I've got p prime p here. Okay, and let's see, then I've got p from the other one with x, again, constant right here, right? Or at least a function that I don't necessarily have to worry about, as long as it stays inside the integral sign, not constant, but and not relative to this this inner product that I'm doing. I can bring it on out. Let's go back to blue, px, and then I've got dp, and I got to keep the wave function inside my integral. And so I guess I've got that. Okay, now you have to remember from last lecture, what is the significance of that thing? And hopefully you realize that that guy is the Dirac delta of p minus p prime, and it allows us to do the p integral pretty simply, doesn't it? So I got the double integral. They're both from minus infinity to infinity. I'm going to be too lazy to write it twice. I've got px here, and I've got dp, and I've got psi just copied right down. Okay, and this integral right here, that one, and not with that, but with that, hopefully you realize it just changes p to p prime every place I need it. Okay, and so I guess I'm going to do that. One thing that the problem also tells you, and it's just giving it to you as a math fact, it tells you what the inner product of x and p is, given in the problem statement. Okay, and so the problem is I've got px the other way. If I flip the order, you should remember what that does is give me a complex conjugate. So now I think I've got an integral from both of them from minus infinity to plus infinity. I've got the Dirac delta of p minus p prime. And if I switch the order of these two things, pointy brackets, x p complex conjugate, that's supposed to be pointy, complex conjugate, dp times psi x t dt. All right, I can erase all this. Other than what it is, this is the momentum space wave function that we talked about. Okay, so go back and remember all of this is that guy. And I think I'm ready to put in the math fact we're told. We're told that this guy would be equal to e to the I px over h bar divided by the square root of 2 pi h bar. Okay, if it was not the complex conjugate, if I'm writing it as the complex conjugate, it goes in negative, doesn't it? Okay, I got dp right here. I got the Dirac delta of p minus p prime, and I got this double integral, both of which are minus infinity to plus infinity, but I'm being too lazy to write both. And I've got this guy right here, the initial wave function, which was the space coefficient, I guess, like a Fourier coefficient. And this integral right here, we're ready to do it right now. If I'm going from minus infinity to infinity, p prime has to be within that range. And so this just allows me to rewrite this with p prime substituted in, okay? And so I guess I've got one integral, minus infinity to infinity, of e to the minus I p prime x over h bar, because I've done that integral, multiplied by psi x t, and then I don't know why I wrote d. That's an x right there, dx. And as I was looking up, I'm like, okay, do I have what I was supposed to be trying to have? Well, I would if I remembered to put that in there like it's supposed to be. And so if you knew that math fact, that this guy right here was that thing, which is something I guess you can prove in a different case. Well, sure enough, we're finding that the momentum space operator could be exactly found from this little process. As I saw question number 5, it really is all hinged on you knowing that math fact. If you don't, not a very useful derivation, but it does cause you to use Dirac orthonormality, see the usefulness of it, that you can turn a p into a p prime. Remember, all of this we started with, since I did that right there, okay, was this momentum space function at p prime. And sure enough, we're finding that this is what it's supposed to be. And so I could drop the primes if I want. Now that's just a dummy variable, and I have proven what I have to show. I think I'm about 5 minutes over, actually I'm more like 8 minutes over, so I better let people go because you may have another class to go to. I'll be in office hours come 3 o'clock this afternoon. Hope a few more people come up and have some questions for me. Otherwise, I'm looking forward to you uploading the tutorial on observables as Hermitian operators by the end of the day today. And I hope everybody is safe wherever they are and you have a great day. We'll talk to you later. So I'm going to stop sharing. I'm going to end unless there's a question, but if you got to move on, I'll hang around here, take questions. But if you got to move on to your next event for the day, go ahead and do that. Not hearing any questions, seeing people leaving, so I'm going to end the meeting.